your notes for AP Calculus on the topic of the summary of the convergence test for infinite series continued. So it says determine whether the series converges or diverges. And here we're not adding any new tests, we're just looking at all the different tests we've learned so far. But this last part that says state the conditions of the test used for determining the convergence or divergence, that's just a long way of really saying to justify our answer. So previously we were stating which tests we were using, but we weren't really formally justifying. So on this first one, -3 to the n over pi to the n plus 1. And one thing to keep in mind, there's not just always one way of one test to use on these. Sometimes you can figure out the same result in using different tests. So I'm going to show you guys what I think is probably the easiest way on each of these, and that's what I put on the solutions to the corresponding homework assignment. But you might find, you might get the same result using a different test, and that might be okay too. If you're not sure, just ask me, and I'll be happy to see if that test also works. So it's not just there's always just only one test you could use. So on this first one, -3 to the n pi to the n plus 1. Well, one thing you can do to rewrite this is you can actually split up this -3 to the n. Notice if you plug in 1, it's -3, 2 is positive 9, 3 is -27. So you can see it alternates. So one way you can test that it alternates here, or see it more easily, it's an alternating series. If you split up this -3 to the n, notice that you could write that as -1 times 3 to the n, like that, because -1 times 3 is the same as -3. And then you can split up -1 to the n and 3 to the n. So it could also be written like this, -1 to the n and then 3 to the n over pi to the n plus 1. And then it's a little more it's a little easier to see that this is okay. This is an alternating series because of that -1 to the n. And the rest of it is what we call the a sub n on the alternating series one. So we're going to use to figure out if it converges or diverges. So in this one, since it's alternating, we'll use the alternating series test. And with the alternating series test, you can first find the limit as n approaches infinity of this a sub n. In this case, 3 to the n over pi to the n plus 1. So when you plug in infinity, you get 3 to the infinity over pi, and plus 1 is negligible, so pi to the infinity. So they're both exponential, but their bases are slightly different. Notice pi is approximately 3.14. So that might not seem like much of a difference, but when you substitute infinity, when you go up to infinity as the exponent, having a larger base, eventually this pi to infinity becomes much larger than just 3 to infinity. Because each time you multiply by pi on the denominator versus this time, each time you're multiplying by 3 on the numerator. So the gap's going to get wider and wider between these two. And whenever the denominator is much larger, these infinite ones, remember that means it's going to equal 0. And that's the first condition that has to be true in order for it, alternating series to converge. Kind of like the the divergence or nth term test, except there it doesn't have the -1 to the n, it's just this part. So this means it might converge. If this was not 0, then you would know for sure by the alternating series test that it diverges. So the next thing you test with an alternating series test is you have to find the first 3 terms. Well, really to see if the terms keep getting smaller. Usually you can tell that by the first 3 terms. So the first term, you substitute the starting number, which in this case is 1. And we're only going to look at the a sub n part. You don't use the -1 part when you're finding the first 3 terms for the alternating series test. Because if you use the -1 part, they're never going to keep getting smaller because they're going to alternate back and forth between positive and negative. So just ignoring the fact of whether they're positive or negative, just this part of it, are they going to keep getting smaller? So the first one, you'd have 3 over pi squared. Then the second term, you'd have 3 squared. You could simplify it to be 9 over pi cubed when you plug into the next integer. Then you'd have 3 to the third over pi to the fourth. So it might be a little hard to tell with the pi's in there to see if these keep getting larger or smaller, but notice the numerator keeps getting multiplied by 3, and the denominator keeps getting multiplied by pi. which is again about 3.14. So that's less than 1. If you keep multiplying by something a little less than 1, notice it keeps getting smaller. So these do keep getting smaller. And usually you can tell that by just the first 3 terms. And if they keep getting smaller, that means, and the limit as n approaches infinity was 0, those are the 2 things that both have to be true for an alternating series to, in fact, converge. If either one of these were not true, if one of these terms got larger here from the first to the second term, or the second to the third term, or this limit didn't equal 0, then it would diverge by the alternating series test. So since we're going to justify these, whenever you're justifying something, it's a more proper form to write as a complete sentence. So we can say the series converges by the alternating series test. First reference the test. Pretty easy. So you do need to know the names. And then you can say, since, and with the alternating series test, if it converges, you have to say 2 things. The first thing you have to say is reference this limit right here. The limit as n approaches infinity of 3 to the n over pi to the n plus 1. Equals 0. And easiest way to show that the terms keep getting smaller is use it right from the definition of the test there, that a sub n is always greater than a sub n plus 1, which is always saying the first term is greater than the second term is greater than the third term is greater than the fourth term, and so on. So the way you can say it for all terms is just to say for all n. That's always going to be true. Terms keep getting smaller. If either one of these was not true, and it diverged by the alternating series test, all you'd have to say, if it wasn't equal to 0, you could just say this limit does not equal 0. And here, if it was the second thing that wasn't true, you could either say a sub n is not greater than a sub n plus 1 for all n, or you could reference the specific terms where it's not small. So if the first term was larger than the second term, you could just say since a sub 1 is greater than a sub 2, or if the second term was larger than the third term, you could say since a sub 2 is greater than a sub 3. Would be a way to justify that it diverges by the alternating series test. All right, let's take a look at another one here. This one, clue, you've got the factorial. So when you see that factorial sign, for most of the factorial ones, the ratio test tends to work best for those. So the ratio test, remember you find the limit as n approaches infinity. And then there's the absolute value sign. And then you substitute in n plus 1 into your formula there. This is you do the a sub n term here. So you substitute n plus 1. So put n plus 1 for that n and for this n. So that would give us 2 to the n plus 1 squared over, and you substitute n plus 1 here plus another one, that's going to be n plus 2 factorial. Now you could put divided by the original, that's how the ratio test is written. But in terms of simplifying, it's easier when you divide by a fraction. This one, the original formula for a sub n, it's the same as multiplying by the reciprocal. So if you want to save yourself a step, you can just write times the reciprocal, n plus 1 factorial over 2 to the n squared. And then to simplify, you can see the n plus 1 and n plus 2 factorials, those reduce, just like if you had 3 factorial over 4 factorial. So it'd be 3 times 2 times 1. This would be 4 times 3 times 2 times 1. So everything's going to cancel out, except for the term that's 1 larger. And that's just 4. It's no longer 4 factorial, it's just 4. So that's what happens here. These reduce out, just leaving you with n plus 2. And then you can start to write down the simplified form before we substitute infinity. So the limit as n approaches infinity absolute value. And then we'll have n plus 2 is on the denominator. And then these have the same base. So remember with the same base, just like if you had x to the 7th over x to the 4th, that would give you x to the 3rd because you subtract the exponents. That's what we're going to do here. Just a little tricky with that n plus 1 squared. We want to take that one, n plus 1 squared, that exponent, and subtract this n exponent of n squared. Well, to simplify it, though, it requires multiplying this one out. The easiest way. So that would be n plus 1 times n plus 1 minus n squared. And then if you square it out, you get n squared plus 1n plus another 1 gives you 2n plus 1 minus n squared. And then you can subtract, you can see the n squareds cancel out here. And leave you with just 2n plus 1. So that's what the exponent becomes. And since the large one was on the numerator, it'd be 2 to the 2n plus 1. And a lot of times on these, the absolute value doesn't end up having an effect, but we'll see on when we get to power series that it is very important to have the absolute value signs there. And then substitute in infinity and see what happens. So we'll have 2 to the 2 infinity, the plus 1 is negligible, over infinity plus 2, again the plus 2 is negligible. So you could tell what this equals right here, or another way to look at this, if you had something larger on the number to compare this to, another way you could write this 2 to the 2 infinity, 2 squared is just 4. So you can even think about it as like parentheses like this. So this would give you, because you would just multiply the exponents anyway. So this is actually the same as 4 to the infinity on the numerator versus infinity on the denominator. And this time, remember exponential ones grow faster than polynomials, even if this was like a infinity to the 100th, this would still be larger eventually. So that's much larger. And when the numerator is much larger, that means your answer is infinity. As opposed to what we saw in the last one, if the denominator is much larger, then it's equal to 0. And the key with the ratio test, and the root test is like this too, you look at if it's greater than or less than 1. In this case, it's greater than 1. That means it diverges. If it was less than 1, it would converge, and if it equaled 1, then you wouldn't be able to use the ratio or root test. So we can say the series diverges by the ratio test. Since well, we can reference this limit we found up here. The limit as n approaches infinity, absolute value. And if you write it this way, or you can write it the original way before we do the reciprocal, either way is fine. Since the limit is 2 to the n plus 1 squared over n plus 2 factorial, divided by the original one, or multiply by the reciprocal is fine too, because it's the same thing. 2 to the n squared over n plus 1 factorial. The importance of that is that it was greater than 1. That's how we knew that it diverges. Again, if it was less than 1, we would say the same thing converges since this limit is less than 1. All right, let's take a look at a couple more here. On this one, when you have something that's a little more complicated and you can tell, well, if you go to infinity, this n squared is not going to matter compared to the 3 to the n, then you can compare it to if that n squared wasn't there, because they're not going to be that much different in terms of whether they converge or diverge. So try to compare it to something similar to it, where we would just have 4 to the n over 3 to the n. And with this plus n squared on the denominator, if it makes the denominator larger a little bit than this one, the denominator larger means the whole series is going to be smaller. So we can say it's always smaller than n. If you can't tell if it's always larger or always smaller than the one you're comparing to, then go directly to the limit comparison test. If you can, though, that means you might be able to use the direct comparison test, which if you can use it tends to be a little bit easier. So, well, let's see what's going to happen with this. 4 to the n over 3, if we plug in 1, we get 4/3. If you substitute in 2, you get 4 squared over 3 squared. Third, 1, 3. 4 cubed over 3 cubed. So hopefully you can tell this one's being multiplied by 4 on the numerator and 3 on the denominator. When it's multiplied by the constant, that's a geometric series. Where r equals 4/3. And remember, with a geometric series, you look and see if this 4/3 is between -1 and 1 or not. In this case, it's not between -1 and 1, so that means it diverges. Okay. So the next thing to see is, can we use the direct comparison test here or not? So this one diverges. In other words, unless it's bouncing back and forth here, diverging means it goes off to infinity. And this one's always smaller than it. Well, if this is an infinite, if it diverges and this one's smaller than it, well, this one also could diverge. It could also be infinite, just not quite grow as fast as this one. That's a possibility. Or it could converge. Since it's smaller, it might approach a specific number, a specific finite number that's not infinite. But we don't know. So this is a case where you cannot use the direct comparison test. If this converged, then it was smaller, then we would know this converged also by the direct comparison test, but it doesn't work in this case. So when the direct comparison test is not valid, okay, so I'll write that here. Whether it's because of this or because you can't tell if it's always going to be smaller or larger than the other one, then just go to the limit comparison test. So you've already got everything you need here. You just have to find the limit as n approaches infinity. The original one, here you don't use the absolute value signs like you do with the ratio test, and you don't plug in n plus 1. Sorry, I just said don't plug in n plus 1, so I actually put plus 1. You just write the original one here, 4 to the n over 3 to the n plus n squared, and then it's divided by the one you're comparing it to, which again, the one we're comparing to, the same as multiplying by the reciprocal, 3 to the n over 4 to the n. And then when you plug in infinity, notice this n squared compared to the 3 to the infinity is going to be negligible, so you'd have 4 to the infinity over 3 to the infinity from here, times 3 to the infinity over 4 to the infinity. In this case, everything reduces out, and you just get 1. And as long as you get a positive number that's not infinite when you do this, that means the limit comparison test tells you these two that you're comparing do the same thing, either both diverge or both converge. So here we can say the series diverges by, first let's talk the limit comparison test. And whenever you're using one of the comparison tests, the limit or direct comparison test, you're always going to have to reference another test too that you used on the one you're comparing it to. Well, let's first take care of the limit comparison test and state why that's valid. So you can say this limit that we just found here, the limit as n approaches infinity of 4 to the n over 3 to the n plus n squared. Again, you can write times the reciprocal or just divided by the original one there. Divided by the original one was, or the one we're comparing it to, I should say, is 4 to the n over 3 to the n. Since that limit, here what we want to say about it, actually I should have left a little more room here, is that it's positive, but it's not, it's less than infinity. So it's easiest probably to write it as a compound inequality, like this. Since 0 is less than this limit, and this limit that we got, in this case it was 1, is less than infinity. So some positive finite answer, something positive that's not infinity, is what has to be true. And we also have to reference the geometric series test, because we used that on the one we compared it to. So we can say, and the geometric series test. Since here, we can say first, when you're using the geometric series test, tell what you got for r. R equals 4/3. And we can say basically like we said there, which is not between -1 and 1. Notice if it was between -1 and 1, all you'd have to say r equals 4/3, then you could write -1 is less than r, which is less than 1, but here it's not. So it's probably easiest to say it in words there. All right, let's take a look at one more. This one's kind of similar in the way it looks here to start with. It's got this 4n plus n to the 5th, except this time, the one with the higher exponent, this is the one that's not going to matter. So let's compare it if that 4 to the n wasn't there. So from n equals 1 to infinity. So if that wasn't there, we would just have n to the 3rd over n to the 5th. In this case, unlike the last one, we can actually simplify that. So we're actually comparing it to the series from n equals 1 to infinity of just 1 over n squared. And again, with that extra plus 4n on the denominator, we can tell this one is going to make the denominator larger, means it's, again, always smaller than this one. So let's say always smaller than. And this time, this one fits the p-series test. See if it's that formula, 1 over n to some constant power, and p is equal to 2. And with the p-series test, be careful, it's almost the reverse in terms of conclusions as the ratio and root test. Here, since this is greater than 1, that's what tells us this converges. Which, versus if it was less than or equal to 1, then it would diverge. Now in this case, we've got this one converging, and we know that means it's not infinite. It approaches a specific number, a finite number. That means this one's smaller than it. So there's no way this can be infinite, otherwise infinity can't be smaller than a specific number. So here's where you can use the direct comparison test. Since this one converges to a specific number and this one's smaller than it, then it also would have to converge to a specific number and not be infinite. So we can say this series converges by the direct comparison test. First state why that works. So here, what you have to say with the direct comparison test is they both have to be positive, which they usually are anyway. 0 is less than. The smaller one you put first, whichever one that happens to be, which in this case was our original one, n cubed over 4n plus n to the 5th. And it actually, the formula itself for the test, I should say, says it has to be less than or equal to this one always, the 1 over. You can use this form, the n cubed over n, or the simplified form. Since that's true, and we also use the p-series test. And the reason for that one was because p equals 2, and we so we're done there since that's greater than 1. Or if it diverges, it would be since it's less than or equal. But if it diverged here with the p-series, we'd have to use the limit comparison test, since this one was smaller than. And that concludes the notes for AP Calculus on the topic of the summary of our convergence test for infinite series. Continue.